Welcome to our presentation titled Learning the Finite Size Effect for In-situ Absorption Measurement. My name is Elias Zea. I'm a researcher at KTH, and I have done this work in cooperation with Brandão from Federal University of Santa Maria in Brazil, Mélanie Nolan from NTNU Denmark, Joakim Andén also from KTH, Jacques Cuenca from Siemens, and Peter Svensson from NTNU in Norway. This work has been financed by the Swedish Research Council. Perhaps the best way to begin is with a typical absorption spectra of a finite sample obtained with the 2-microphone method, compared with the Delany Bazley Miki model using a transfer matrix method. What we see in this figure is the result of the finite size effect. The discrepancies in the spectra are most noticeable in the lower frequencies and have been attributed to the diffracted waves coming from the edges of the sample. Several studies have compared experimental data with boundary element simulations in order to describe and account for this effect, but fewer studies have attempted to characterize it experimentally, given the limitations of current in-situ methods. This is why, in this work, we have proposed to make use of machine learning in order to mitigate the finite size effect and provide a reliable estimate of the absorption spectrum, just as if the sample was infinite. In-situ measurements of the sound absorption aim at characterizing the absorptive properties of the material when it is placed for its intended use and location. These methods comprise subjecting the absorber to acoustic waves emitted by a sound source, either omnidirectionally or with a specific incidence angle, and recording the sound pressure at a number of microphone positions. Thereafter, the sound pressure is mapped to the absorption by means of a suitable data processing method. For instance, plane wave decompositions, spherical wave decompositions, etc. This is contrary to standardized methods in which the absorber is either placed in an impedance tube, which constrains its geometry and size, or it is subject to a diffuse field in a reverberation room, which is often hard to replicate across laboratories. In addition, standardized methods cannot describe the absorption of the sample in terms of the incidence angle of the sound, something that free-field and in-situ methods can do. Nevertheless, in-situ methods make an important assumption, that the sample is large enough compared to the acoustic wavelength, such that the contribution of edge diffraction to the sound field can be neglected. The finite size effect is the consequence of this assumption not being valid in practice, because absorbing materials have finite size, which ultimately introduces a bias in the measurements. This bias has been attributed as the cause of oscillatory discrepancies, as the ones we saw in the first slide, between the model and experiment, particularly in the low and mid-frequency regime. Therefore, it is of great interest to look for strategies that can mitigate these discrepancies. An emerging approach to mitigate the bias introduced by modeling assumptions is to use machine learning, often regarded as a data-driven approach. In this case, the idea is to dismiss the assumption of absorber size and let an optimization algorithm learn the necessary relationships directly from the data. Today, we will focus on supervised learning, in particular on convolutional neural networks, known as CNNs. CNNs are most suitably used to process image inputs, which allows them to extract features at multiple scales or resolutions. These networks have been used successfully in a number of acoustic problems, such as the estimation of porous material parameters, room acoustics parameters, direction of arrival, as well as near-field acoustic holography. The key idea is to map inputs to outputs by means of using convolution operations, affine functions, and nonlinear activations. CNNs are trained with known inputs and outputs, often referred to as labels, such that the network parameters mu can minimize the error between the known labels y and the outputs generated by the network y star. In order to generate the known inputs and labels, we have used a simplified boundary element model. The absorber is a rectangular sample of thickness d and constant impedance across the surface. We assume the sample is locally reacting and lies on a baffle with rigid backing. The characteristic impedance and wave number of the material are calculated with the Delany Bazley Miki model, and a transfer matrix method is used to calculate the absorption spectra. These spectra correspond to the labels of the CNN. The source is emitting stationary waves at 5 frequencies, spanning 125 to 2000 Hz, and it is placed in a hemisphere 1.5 meters away from the center of the sample, parameterized with incidence angle theta and phi. The receivers comprise a single layer array of 12 × 12 probes with 2 centimeter spacing. The input data for the CNN is the magnitude of the array pressure at the 5 frequencies, that is, a tensor with dimensions 12 × 12 × 5. The sound pressure model is written as a Helmholtz-Huygens integral, which amounts to the sum of the contribution of the source in free field, the mirror source, and the absorption term. More details on the numerical implementation of this integral can be found on the paper. For benchmark comparisons, we use the well-established 2-microphone method. This method makes use of transfer functions between 2 microphones above the sample in order to determine the frequency-dependent reflection coefficient and thereafter calculate the absorption coefficient. The microphone distances used in this paper are 1 centimeter and 3 centimeters, and the pressure signals are taken from the boundary element model. The proposed methodology consists of a convolutional neural network. The main idea is to map edge-diffracted pressure fields to absorption coefficient spectra as if the sample is infinite. In other words, to mitigate the finite size effect. The architecture consists of 2 convolutional layers, COM1 and COM2, both with kernel sizes 2 × 2 and stride 1, an increasing number of channels, 16 and 32 respectively. The activation functions are rectified linear units, also known as ReLU functions. The output of the COM2 layer goes into a max pooling, which takes the maximum value and downsamples the data. Thereafter, the features are flattened and fed into a fully connected layer, FC1, of 100 neurons with ReLU activation functions. The output is another fully connected layer with 5 neurons and sigmoid activation functions. Sigmoids are meaningful here since the absorption coefficient has values between 0 and 1. For training and validation, we generated a total of 285,120 cases, each consisting of the array pressure at 5 frequencies, as you can see on the right, together with their corresponding absorption spectra. The cases are derived from combinations of simulation parameters such as sample size, flow resistivity, thickness, and source incidence angles. The script was run on Google Colab using the free GPU resources, and the TensorFlow library was used to craft the neural network. The training and validation losses are shown here as well. It can be seen that the validation loss converges at around 100 epochs. For testing, however, we have used the CNN trained for 200 epochs. With the GPU, it takes around 20 minutes to train this. We have divided the testing into 2 different conditions, interpolation and extrapolation. In both conditions, the test cases generated had not been seen by the network. That is, cases were different than the ones used for training. Let's start with the interpolation test. We generated 15,000 cases by taking 15 fixed sample sizes and 1,000 uniformly random simulation parameters. In the case of interpolation, all simulation parameter choices are within the range of the parameters of the training set. The absorption spectra of 4 example cases are shown in the right. The left column shows cases with thin, not so resistive samples, while the right column shows cases with thick, resistive samples. The top and bottom rows correspond to cases with smaller and larger sample sizes. The key results here are the usual oscillations in the spectra obtained with the 2-microphone method. On the other hand, the CNN shows reasonable agreement, except for the underestimation on the top left case. We suspect this is due to the sensitivity of the network to particular simulation parameter choices, and further research is needed to understand this better. For the extrapolation test, we generated 15,000 additional cases by taking again 15 fixed sample sizes and 1,000 uniformly random simulation parameters. In this test, the source distance was varied between 1 and 2 meters, as opposed to the 1.5 meter distance that was used to generate in the training set. In other words, we test the capacity of generalization of the network to conditions outside those presented in the training set. The absorption spectra of 4 example cases are shown in the right. The top and bottom rows correspond to cases with smaller and larger sample sizes. The top left and bottom right correspond to source distances closer than the one of the training set, while the top right and bottom left correspond to source distances farther than the one of the training set. The predictions with the 2 microphone method are most accurate in the bottom right case, and otherwise yields oscillatory deviations in the spectra. In contrast, the CNN demonstrates a reasonable agreement even when the source distance is different from the one in the training set. This indicates the potential of the network to generalize to unseen cases. As an additional test, we examined the sensitivity of the network to source distance. We then clustered the extrapolation test cases with respect to source distance into 11 intervals spanning from 1 to 2 meters. The mean absolute and mean square errors are shown in the plot to the right. These errors increase faster as the source gets closer to the sample, compared to the slower error increase when the source moves away from the sample. We suspect this behavior might be caused by the presence or absence of near fields, but further research is needed to verify this. Lastly, the error increase is rather gentle, which suggests that the network is not overfitting too much. To summarize, we have discussed the relevance of addressing the finite size effect for in-situ absorption measurements, and for this matter, we have proposed a data-driven methodology to mitigate this effect by means of convolutional neural networks. Although this is a preliminary study, it already shows very promising results, and further work can be done to investigate the performance of single versus multiple frequency networks, a sensitivity analysis of the simulation parameters, as well as an experimental validation. Thank you for your attention, and I look forward to discussing with you during the Q&A session.